Our next topic is intermolecular forces. So I view this as sort of the keystone to this whole first part of the class. We're going to take together everything that we know about bonding, the different atomic properties, and put it together here to now understand the different properties of solids, liquids, and gases. Okay, so next I'm going to show an animation of four different substances here, A, B, C, and D, and you want to try to determine which is which temperature. So here's the animation. Okay, so hopefully you have D at the lowest temperature. That's the solid with the particles moving around very, very slowly. A, the gas with particles moving incredibly fast, would be the highest temperature. But B versus C. C is a gas if we look at the phase, but if you looked at the speed of the particles are moving pretty slowly. So which is the higher temperature? Well, it turns out that C would actually, even though it's a gas, C would be a lower temperature compared to B. It's perfectly possible to have gases that are quite cold. Think about sort of liquid nitrogen after that boils off. It was going to be very, very cold, still about 77 Kelvin as it boils off, with the gas particles moving very, very slowly, but it would still be a gas compared to, your banana or something like that you're sticking in it that's maybe room temperature. So it's really speed that's the key factor. To understand this a little bit more rigorously, we can look at this thing called kinetic molecular theory. So we know that substances don't boil or freeze at the same temperature. They have these different properties. And these really need to be related to our molecular properties that we've been studying. How? Well, just like we talked about in the last section, matter is made up of these tiny particles. So atoms, molecules, or ions. They're constantly moving around with the distribution of speeds, and our temperature is proportional to the average kinetic energy of the particles. So from 0 Celsius to 1000 Celsius to 2000 Celsius, the speed of the particles is increasing, which is increasing their kinetic energy. What about those particles? How are they interacting to form solids, liquids, or gases? Well, at short distances, all particles repel. That's just a consequence of their electron clouds overlapping and the electron clouds repelling each other strongly. But all particles are different in their attractive forces. There's always some attractive forces as particles come together, but the different types of particles have very different strengths of attractive forces. Here's another illustration of that. Again, these two particles here are a little bit far apart. They could be any particles. Maybe I'll call them xenon atoms just to give some example, but they could be molecules or ions, say. They're attracted together, and so when they're attracted together, they can lower their energy by coming together closer. If they start far apart, we can lower our energy until we get to this most stable point where attractive and repulsive forces balance. Now, if I want to increase the energy of this substance, I have to add energy if I want to take those particles that were close together, maybe in the solid state, and pull them apart. So this is sort of a negative potential energy, just like the ground state of an atom is this lowest energy state. The lowest energy state here would be the solid, where they're the ideal distance apart. So those attractive forces are holding our atoms or molecules together in, say, the solid state. The stronger the forces, the more energy we're going to need to separate the atoms or molecules. Where are we going to get that energy? From that kinetic energy. As we crank up the temperature, we give the particles more energy that they can use to overcome those attractive intermolecular forces. So the key idea, this is a review of our kinetic molecular theory. Gases are in that constant random motion, conserving their energy with kinetic energy proportional to temperature, which you may have studied in a prior chemistry or physics class. When the average kinetic energy is greater than the energy of attraction between the molecules, they won't stick together and we'll get to that gas phase. So in conclusion, the state of matter that we get for different particles depends on the strength of those intermolecular forces. Those don't really depend on temperature, but they do depend on distance. The particles are going to have a low energy if they're in that ideal distance apart, and the energy will increase as we pull the particles further apart. Now, average kinetic energy is the other factor. That just depends on temperature. So there's this trade-off between the kinetic energy of the particles that we can increase by increasing temperature and the strength of their intermolecular forces. So if the kinetic energy of the particles, the temperature, is greater than the intermolecular forces, then we get the gas state. If it's similar to the strength of those intermolecular forces, we're in the liquid state. And if we have a small amount of kinetic energy compared to the strength of those intermolecular forces, we end up in the solid state. Okay, here's a application. At a given temperature, remember, all molecules have the same kinetic energy. So based on that, we have this information. Cl2 is a gas, Br2 is a liquid, I2 is a solid. How can you order these in terms of their strength of intermolecular forces based on this experimental data? Okay, so we're at the same temperature, so we know we have the same kinetic energy. And the state we're in just depends on how much energy, how strong the intermolecular forces are compared to that kinetic energy. So let's go I2 maybe to start with. I2 is a solid. That means the IMFs here are greater than the kinetic energy. So this one is going to have the biggest intermolecular forces. Its intermolecular forces are so strong that we're still in the solid state, even at room temperature, where we have a moderate amount of kinetic energy. Similarly, Br2 is a liquid. That means that the IMF here of Br2 is about equal to the kinetic energy. The kinetic energies are the same, so this is a little bit lower intermolecular forces. And Cl2, which is a gas, that means that even at room temperature, we're at this case where the intermolecular forces here are less than the kinetic energy, and we have enough energy at room temperature to pull those particles apart into the gas phase. Okay, so next we're going to look at three types of intermolecular forces. Hydrogen bonding, which we can view as a special strong type of dipole-dipole force, dipole-dipole forces, and dispersion forces. So this is one of those key slides that I would write out in your notes. We'll work through this bit by bit, so you can sort of build this out as a table. What type of intermolecular force, what types of molecules have these forces, how strong are these forces in different cases, and write out this key information as we go through it in the notes. One key difference to highlight at the beginning is the difference between covalent ionic bonds compared to intermolecular forces. So H2O, say, this is a covalently bonded molecule, and these lines, right, are pairs of electrons holding the atoms together into the molecule. If we want to break those covalent bonds, we need to put in a huge amount of energy, in this case 930 kilojoules, to break all of those OH bonds and form free atoms. You can only do that at incredibly high temperatures or with lasers or something else where it can add a huge amount of energy. Now, intermolecular forces, on the other hand, are much easier to overcome because they're much weaker. It's much less energy, so it only takes about 41 kilojoules to take 1 mole of hydrogen, 1 mole of water, and turn it from the liquid state, where they're close together, doing this, what we'll call hydrogen bonding in a second, to H2O in the gas phase, where the molecules are flying apart very fast and not stuck together. Note that there's still molecules, though. There's still those covalent bonds. It would take much more energy to take that H2O gas and break it apart into this state. So very important to note the difference here. Intermolecular forces are between two different of these molecules. As they come together, they can interact. Okay, let's start with some experimental data to motivate what we're doing here. So take a second to try to draw a few observations from this chart showing the boiling point of different molecular hydrides. These are all covalently bonded and have different intermolecular forces. Okay, so I'll start drawing some conclusions here. Maybe I'll start with the one that we're going to focus on first. So if we look right here, this is a important part of the graph. Note that our normal trend here as we go down the graph is we have an increase in boiling point. So that would be one observation. I'll put that one last. But note that these three molecules here, NH3, HF, and H2O, have particularly high boiling points. So that's one of our first key observations. I'll do number 3. You'll see the order in a second, the reason for it. Number 3 is this general trend that as we go from period 2 to period 3 to period 4 to period 5, we go to bigger and bigger atoms that we're bonding to hydrogen. We get bigger and bigger boiling points. We'll explain that in a minute. Number 2, hard to draw this conclusion, but let's look at it. If I look, say, in this second row here, something like that, and it holds through for the other ones here as well, note that the thing in the carbons group 4 here, so CH4, SiH4, GeH4, and SnH4, they all have a bit lower boiling points compared to the other 3. We could probably draw more conclusions as well, but that's a good starting point. Note that these compounds vary tremendously in their boiling points, from negative 200 Celsius all the way up to water of 100 Celsius. That means that we're looking at molecules that have very, very different strengths of intermolecular forces. Okay, so first let's explain that observation number 1, the high boiling point of H2O, NH3, and HF. Well, that's going to come down to our first intermolecular force, hydrogen bonding. So this is a special strong dipole-dipole force. The idea is that when we bond hydrogen to a very electronegative atom, what we get is the hydrogen has a bit of a partial positive charge. The oxygen has a negative charge, or similarly the nitrogen or fluorine would have that negative charge. Then when we bring those two things together, remember we're thinking about the forces between two of these different molecules, we bring the partial positive on hydrogen, the partial negative on oxygen, positive and negative attract, so we get a strong interactive force between the partial positive charge on hydrogen and the partial negative charge on oxygen. It turns out this lone pair is also quite involved in this process. We need that lone pair. It donates some of its electrons to the hydrogen. So hydrogen here we're donating this hydrogen, and there's this lone pair that's accepting the hydrogen bond on the electronegative atom. So it's easy to know which molecules have this, only things with an OH, NH, and FH bond. So again, that first observation, let's come back to it. Well, water, HF, and NH3 buck that trend because they have additional strong hydrogen bonding intermolecular forces. So we can see these are very, very strong intermolecular forces and cause those deviations from the trend. None of the other compounds in this table have hydrogen bonds, and so these are much higher than the other ones in general. Note the second thing too, stronger intermolecular forces is going to mean a higher boiling point. But what about if we're not thinking about the solid? If we're at the same temperature, a stronger intermolecular force is going to be a higher boiling point and also a lower vapor pressure, right? Because the vapor pressure is how much of that substance can escape into the gas phase at a certain temperature. The stronger the intermolecular forces, the harder it is for that molecule to break out of the solid or liquid and go into the gas phase. Okay, our first exercise, which of these can form hydrogen bonds? Some of these are relatively straightforward, some of these are a little bit harder. Argon is a freebie, there's no hydrogen, so it can't form a hydrogen bond. HF, if we think about its Lewis structure, that's a hydrogen bonded to fluorine. So yes, that can form hydrogen bonds. NH2Cl, for these other ones, it is useful to really go to the Lewis structure because remember, we do need an HF, NH, or OH bond. So we need to make sure the oxygen or nitrogen or fluorine is actually bonded to the hydrogen directly in the Lewis structure. NH2Cl does fit that, though because the nitrogen is in the center, that will have hydrogen bonds. CH4 doesn't have one of those electronegative atoms, so that can't have hydrogen bonding. CH3CH2OH, that, if you remember what that skeleton structure looks like, that's an O bonded to H on the end of it. So yes, that will have hydrogen bonds. CH3OCH3 though, well, if we draw out the skeleton structure there, CH3, O, CH3. Technically, there's these two lone pairs on oxygen to get it to a formal charge of 0. But even though this has an oxygen and it has lots of hydrogens, there's no oxygen bonded to hydrogen in that molecule like there is here. So this CH3OCH3 does not have hydrogen bonding. Hydrogen bonding is an incredibly powerful intermolecular force. It holds DNA together in that beautiful double helix state, it also explains our properties of water. Why, unlike most other molecules, ice floats on top of water. Why is that? Well, ice is actually less dense than water because that perfect arrangement of water molecules is in this hexagonal crystal structure, where there's actually a lot of empty space between in the inside of those hexagons in ice. So ice has these perfect hexagons. It's a little bit less dense because of all this empty space. Water, when the hydrogen molecules move past each other, or the water molecules move past each other, is actually able to fill those gaps in and is a little bit denser. So very important thinking about the properties of water. Another key property here is that very high boiling point for such a small molecule. We saw that on our table. It also has a very high heat capacity. It takes a lot of energy to change the temperature of water because it can store energy in so many ways in all these hydrogen bonding interactions between those different atoms. An illustration of the point we made on the last slide, normally the solid, the particles are closest together, lowest in energy, the liquid they're a little further, gas they're further still, but in ice, the ice here is the lowest in energy, making those perfect hexagons. Cold water is a little bit, the particles are actually a little bit closer together. We push into those hexagons a little bit and make it a bit denser. Hot water does eventually become a little bit less dense there. So going back to our summary, we've now got our first key intermolecular force. Let's look next at dipole-dipole forces. So this, remember our observation was that observation number 2, that things like SiH4, CH4 have anomalously low boiling points compared to the other entries in that table. Okay, so to understand that, let's look at what dipoles are. So an electronegativity difference results in an equal distribution of electron density, which causes our bonds in each particular molecule to be polar. So HF is an example. The more electronegative atom has a partial negative charge. The less electronegative atom has a partial positive charge. That gives us a dipole moment. It's this arrow pointing from the positive charge, or the partial positive charge, to the negative charge, or partial negative charge. So from the less electronegative to the more electronegative element, because the more electronegative element pulls those electrons tighter. We can measure that by putting an electric field and watching the dipoles line up to minimize the energy. So if we just have a diatomic molecule, there's only one bond. So if the atoms are different electronegativity, if we have a polar bond, that will be a polar molecule. HF is polar, 1.86 is its dipole moment. ClCl is a nonpolar bond. Each atom attracts the electrons equally in that bond, so the dipole moment is 0, and we call that nonpolar. For polyatomic molecules, though, we need to look at each bond individually and sort of add them up. So something like HCN, we can see this dipole moment going from H to C, another dipole moment going from C to N. Overall, then, these two arrows add up, sort of tip to tail, just like you sort of add vectors in math or physics class. And we get this overall dipole moment from the left to the right. But something like CO2 here, we have a dipole moment going to the left, a dipole moment going to the right, but they're equal and opposite. So when we add those up, we get no net dipole moment. And so that's really important. There's no net dipole moment here, so there's no partial negative and partial positive side of this molecule, and so we can't do that alignment of negative and positive to minimize our energy. So for these other shapes, you just sort of have to look at the dipoles and see whether they cancel. If you think about like a tug of war here, there's no winner in this tug of war because the poles are equal and opposite. Other shapes, a common thing that you might have seen in a prior chemistry class that normally works out is that if a molecule has lone pairs, there's a tendency for it to be polar. And if there's no lone pairs, it has a tendency to be nonpolar. That's because if we have lone pairs on its central atom, that typically makes the shape asymmetric here. So we have like a bent geometry here. These poles don't cancel out in OF2 and we get a dipole moment. If there's no lone pairs, we typically end up in a symmetric shape like BCl3, and those poles exactly cancel out and we get a nonpolar molecule with no dipole moment. So going back to our example, CH4 is shown here. CH4 is this tetrahedral geometry. This is CCl4, but CH4 would also have the same shape. And there's going to be no dipole moment there because those poles would exactly cancel out. And so CH4 would be nonpolar, whereas the other molecules, like, to take an example there, HCl, is going to be polar. Cl is more polar, or Cl is more electronegative, and so that will be a polar molecule compared to CH4, which is nonpolar. We said normally that rule that lone pairs on a central atom make it polar, but not always. So XeF4 here has 2 lone pairs on that central Xe, along with those fluorines. And even though it has lone pairs on a central atom, remember that this ends up, those lone pairs are straight up and straight down on opposite sides, and what's left over is XeF4, the square planar molecule, and these poles are still going to exactly cancel out. So the 2 lone pairs here sort of cancel each other out, and we get a perfectly symmetrical shape. But usually it's the case that we're going to end up with things that are asymmetrical with lone pairs, and therefore a polar molecule. Okay, one other type of molecule that we work with a lot in this part of the class are those organic molecules where we have the skeleton structures, right? So something like CH3OCH3 or C3H8, right? We might write that out as CH3CH2CH3. What about those molecules? Well, in organic molecules, we have hydrogen, carbon, and nitrogen and oxygen are the other very common atoms in organic molecules. The nitrogen and oxygen are what we call polar functional groups. When you have one of those atoms, you have a big difference in electronegativity, 0.5 for CH and 1.0 for a CO bond. That makes the oxygen part of the molecule very partially negative and gives you a dipole moment in the molecule. So in dimethyl ether with that oxygen, we have a net pull towards the oxygen in the molecule. These are sort of the key polar bonds, those 2 COs, and we get a pull from the bottom of the molecule to the top, and a relatively big dipole of 1.32. So if you have an electronegative atom, it will typically be polar and have dipole-dipole forces. Propane, on the other hand, with only C and H, there's very little difference in electronegativity between these two atoms, and those pulls that there are going to basically cancel out with no lone pairs and a symmetrical type of shape. So this has a dipole moment of, in this case, about 0.08, but really basically 0. And we'll just assume these are basically completely nonpolar and don't have dipole-dipole forces whenever we have a hydrocarbon, so just C and H in the molecule. We can see the difference in the boiling point. So propane here doesn't have dipole-dipole forces, and so it has a bit lower boiling point. Dimethyl ether has these extra dipole-dipole forces, which causes it to have a bit higher boiling point. Not a huge difference, but a little bit higher because of those extra forces. Here's some examples of dipole moments of different molecules. Dipole moment, the definition is it's charge times distance, so sort of the sides of the partial positive and partial negative charge, times the distance separating the partial positive and partial negative. The different dipole moments typically here sort of between 0 and 2 roughly for common molecules. The way you can sort of get a sense of the size of the dipole moment is the electronegativity difference between the two atoms, right? So HF is the biggest difference in electronegativity between two atoms, and it's the biggest dipole moment. H2O is also a pretty big difference in electronegativities, and it has the biggest, the next biggest dipole moment. Not a perfect correlation because some of it depends on how many things you're adding up in the shape. What is the effect of those dipole-dipole forces? Well, when we form the solid or the liquid, we're going to have the partial negative parts of the molecules line up with the partial positive parts of the molecule in such a way that we get these attractions. So we put positive and negative close together, we have these attractions here. There's also some repulsions, but since they're further away, they're weaker repulsions. So we get a net attraction when we line them up in this way. Okay, so let's look at another example here. We have ICl versus Br2. ICl is a polar molecule with these two different atoms. Br2 is nonpolar. We can see the effect is that ICl has a bit higher boiling point, in this case about 40 degrees higher. We can also see that effect in terms of the vapor pressure at 25 Celsius, right? The stronger the intermolecular forces, the lower the vapor pressure, because it's going to be harder to pull these particles out of the liquid into the gas phase. Okay, for our next exercise, take a look and do this analysis to determine if we have a dipole moment, polar or nonpolar, and which of these then can have dipole-dipole forces. Okay, for the sake of time, I've drawn out your Lewis structures, but again, you do need to be able to do that to determine whether things are polar. Don't skip that step if it's necessary. Okay, with the Lewis structures here, let's do our analysis. So H2O, this one we wouldn't necessarily need to. We could argue this. This does have hydrogen bonding. And remember, hydrogen bonding is a special strong type of dipole-dipole force. So if a molecule does have hydrogen bonding, it is going to be polar and also have dipole-dipole forces as well. But let's show what the analysis looks like as here, right? This has a steric number of 4, which gives it tetrahedral electrons and a bent molecular shape. So the actual H2O molecule looks like this with this bent geometry. Oxygen is more electronegative, and so these dipoles do not cancel out. We have a net pull sort of from the bottom to the top, and we have a polar molecule. Okay, what about CS2? So CS2, remember we have those electronegativities to look at. So CS2, this one actually we wouldn't even need to draw out the Lewis structure because C has an electronegativity of 2.5 and S also has electronegativity of 2.5. So they have the exact same electronegativity, so the bonds are not polar. And this is then going to be a nonpolar molecule. So if there's no difference in electronegativity, there's nothing else left to do here. I maybe jumped the gun drawing out the Lewis structure. If there were poles, they would exactly cancel because it's this symmetrical shape, but there's no poles here. These actually share their electrons equally because they have the same electronegativity. Okay, for SO2, now this one here, we do have a difference in electronegativity of 1.0. There's no hydrogen bondings or something, so we do just have to look at the Lewis structure. We see that lone pair on the central atom, which means we should be suspicious that this is polar. We can look at the VSEPR analysis to double check. This has a steric number of 3 for trigonal planar electron density, and the molecular shape is there's 3 things around that central atom. One is a lone pair. They're arranged in that perfect triangle, and that makes the molecular shape this bent with roughly 120 degree or a little bit less than 120 degree bond angles. Oxygen is more electronegative, so it pulls the electrons in more, and we have this sort of picture where the oxygens pull the electrons more, and there's a net dipole pointed towards the oxygens. This will be a polar molecule with a net dipole moment. The last one, CH4. CH4 we've looked at in a couple different ways. One, we could just say this is a hydrocarbon, just hydrogen and carbon, so there's no net dipole moment, right? We showed that previously. Just highlighting that point from before, that hydrocarbons are always nonpolar. Again, our key recipe is that to make a polar molecule, we need polar bonds, a difference in electronegativity, and then we need those individual bond dipoles not to cancel. So that depends on the shape, where normally a lone pair will help make the molecule asymmetric so these poles don't cancel. Okay, for the next half of them, SF4, if we look at the electronegativities, very different electronegativities between those two atoms. So yes, we do have polar bonds. Are those bond dipoles going to cancel? We have that single lone pair on the sulfur. That means that this will be polar. Let's double check that by analyzing the shape. This has a steric number of 5, 4 bonded atoms plus 1 lone pair. That gives us a trigonal bipyramidal electron geometry around the SF4. 4 of those things are sulfur atoms, and the lone pair goes right in the plane here. And so while the up and down pulls don't cancel, we have this pull, sort of 2 pulls here to the left that aren't going to cancel because the lone pair is coming the other way. So this is going to get a net pull from sort of the sulfur to the fluorine like that, and that will give us our polarity. Next, SF6. Well, SF6 has a perfectly symmetric type of shape. There's no lone pairs, so we're going to expect this to be nonpolar because it doesn't have those lone pairs. If we analyze it fully, the steric number is 6. That's an octahedral shape, so X, Y, and Z axes. Fluorine's on all of those positions with a sulfur right in the center. So the up and down cancel the left and right, and the sort of in and out of the board also perfectly cancel. All those poles exactly canceling out. Sort of like a very equal tug of war game. NH3, we can identify that this thing does have hydrogen bonding because of that NH bond. So remember that hydrogen bonding is a special strong type of dipole-dipole force. So yes, this molecule is also polar and has dipole-dipole forces too. We can't have a molecule that has hydrogen bonding without also having those dipole-dipole forces, because this is just a special strong type of that. If we did the full analysis, we would also find that the poles don't cancel with this type of geometry here. Trigonal, pyramidal is the overall shape of NH3. For CH2Cl2, let's look at the polarity there. So no hydrogen bonding. We have to actually look at what the 3D shape looks like. This thing here, if we think about it, has a steric number of 4, and so it's going to be tetrahedral. Does it have polar bonds? Well, the Cl to C bond is relatively polar. The electron negativities here 2.5, 2.1, and 3.0. Looking at it on 2D here, we might say, okay, maybe these poles are going to all exactly cancel. But if we think about the 3D shape, since it's tetrahedral, that's this type of structure, where I might have my Cl's there and my hydrogens here. And so these poles are not going to cancel. We're going to have 2 poles here pointing towards the chlorines, and these hydrogens, the poles are going to point towards the away from the hydrogen towards the carbon, and we're going to get a big net pull sort of going from the center up and to the right in the molecule, adding up all those individual poles. Okay, so now we've explained the effect of dipole-dipole forces. Now we're on to the last one, dispersion forces. So this is going to answer that point number 3 we had. Why, as a general trend, when we go to larger and larger molecules on the periodic table, from like CH4 to SiH4 to GeH4 and so forth, we see the boiling point increase with size. That's going to be because of our last one, dispersion forces. Dispersion forces seem a little bit hard to wrap your head around why they exist and why they're so strong. What happens here is that the electrons move around and we get these instantaneous dipoles. In response, the electron distribution of nearby molecules shift as well. So these are called induced dipoles. It's just temporary dipoles, even in nonpolar molecules, or in polar molecules for that matter. They're in all molecules. The strength of the force depends on the polarizability of the molecule. That's how easily those electrons can actually shift around. In general, the larger the electron cloud, the more those electrons can slosh around, and the larger these London dispersion forces are. So here's an example. A little bit unconvincing, but this is how it works. Let's say we start out with the electrons here, perfectly symmetrical around the atom, but when we bring a dipole next to it, we get in it a dipole-induced dipole force. So there's a partial negative over here, and that induces these electrons to slosh around to make a partial positive nearby, because that will lower our overall energy. The easier these electrons are to slosh around, the bigger the partial positive I'll get and the stronger the force. The same thing happens here. These dispersion forces are induced dipole. Just temporarily we get an instantaneous dipole here. The electrons slosh around just to make a positive charge here. The electrons on the neighboring particles slosh around to make a partial negative charge there. It doesn't seem like it's going to be a big effect. And it's not for very small molecules, but as the molecules get big, this effect dominates just because it always increases as the number of electrons and the size of the electron cloud gets bigger and bigger and bigger. So just to give an example of some of the data here, look at how the boiling point of the halogens increases here. If we go from F2 to Cl2 to Br2 to I2, we're cranking up the size of these molecules, the size of the electron clouds and the number of electrons. And the boiling point increases really dramatically from negative 188 to negative 34 to 58 to 184 I2, even though it's nonpolar, it doesn't have hydrogen bonding, it just has dispersion forces. It has an incredibly high boiling point just because it has so many electrons, a total of 106 electrons here, all sloshing around in that big I2 molecule. So the larger the electron cloud, the more polarizable, and the larger the dipole forces, and the larger the intermolecular forces. So I2 has very strong intermolecular forces, even though it's just dispersion forces. Okay, so here's an example, again, the power of these dispersion forces. Br2 versus ICL. We can see that ICL, the extra dipole-dipole forces, gave us a little boost of about 40 degrees to the boiling point. But if we think about the effect of the number of electrons, H2 is just 2 electrons compared to Br2 is 70. We've made a big increase in the size of the electron cloud, and we made a huge increase in the boiling point, 312 degrees. So huge effect from dispersion forces. Take a second to look at this data here for the different sort of halogen hydrides, and see if you can answer the example question here. Okay, so which molecule has the strongest dipole-dipole forces? That's the one with the biggest difference in electronegativity. So HCl is going to have the strongest dipole-dipole forces because it has the biggest polarity. Now, dispersion forces, well, dispersion forces depend on the size and the number of electrons. So HI has the biggest dispersion forces. What about the total IMFs? Well, that we can see based on the boiling point. So it turns out that the boiling point is increasing here. Even though the dipole-dipole forces are decreasing, the bigger dispersion forces are winning out. And so which one has the biggest total IMFs? It happens to be HI, because we can see that it has the highest boiling point. Higher boiling point equals stronger intermolecular forces. The most important force here in determining these boiling points among these three are those dispersion forces, because that's the effect that happens to win out. Okay, here's our last problem, exercise 3, in 2 parts. Okay, I'll try to go through this as efficiently as we can, thinking about when we do need to write out the Lewis structures and when we can just sort of skip right to the answer. So the first one, N2, that one, since it's just nitrogens, we know that there is no way it can have hydrogen bonding or dipole-dipole forces because it's perfectly symmetric. So this can only have dispersion forces. OCS, we did the Lewis structure of that before, so you can pull that up before. That will have dipole-dipole forces because we've got a sort of asymmetry here. This oxygen is very electronegative, so these poles are not going to cancel. We'll have a pole here, a smaller pole this way, or actually no pole over here because these have the same electronegativity. So just a pole sort of from C to O. That will make it polar. And so because this is polar with that asymmetrical pole, it's going to have dipole-dipole forces and dispersion forces. Everything has dispersion forces. That's sort of a free point for all of them. NH3, we've looked at that one before as well. Since that has that NH bond, that means that it's going to have hydrogen bond, dipole-dipole, and dispersion forces, all three. For D, the easiest way to identify this one is to recognize that this is just carbon and hydrogen. This is a hydrocarbon, and hydrocarbons are always nonpolar. So that's just dispersion forces. SF4 we analyzed before we decided that that was polar, so it has dipole-dipole forces and dispersion like all molecules. For F, that HBr bond is polar because there's a difference in electronegativities, so we have. Okay, then for G, the easiest way to get this one is to recognize that this is an organic molecule, but it does have that electronegative atom in it. So it's C, it has this oxygen in the middle. That oxygen in the middle is going to make it polar. Does it have hydrogen bonding? No, right? If we look at what that sort of Lewis structure looks like, it's got all the hydrogens attached to carbons. So it's just going to have dipole-dipole and dispersion forces. Remember that this has sort of a bent type geometry around that central atom, so dipoles won't cancel and we'll get a polar molecule. Okay, for this one, we ask this type of question a lot, and we might ask you to give a full explanation or compare the size of each type of IMF. You always sort of want to think about all these steps when you're doing these type of problems. What are the IMFs in each, comparing the size of each IMF, and then add them up to get the total IMFs. Whichever one has the larger total intermolecular forces is going to have the higher boiling point or equivalently a lower vapor pressure. For A here, OCS has dipole-dipole and dispersion forces. CO2 has dispersion forces only. Now I want to compare the size of each IMF. Okay, to do that, let's now look first at dispersion. We always need to compare dispersion forces because all molecules have them. CO2 has 22 electrons versus OCS has 30. OCS is a little bit bigger, so OCS has a little bit stronger dispersion forces. Then OCS also has those extra dipole-dipole forces. So as a result, OCS is going to have a little bit stronger IMFs and therefore have a higher boiling point. Probably the key reason here are those extra dipole-dipole forces, although dispersion forces are also going to contribute too. So that's our first comparison. Let's look at the next one. So for this one, both of these substances only have dispersion forces because they're nonpolar. Nope. Same atom, so just the exact same electronegativity for each. So just dispersion forces, if we count the electrons, we have 70 electrons in Br2 versus 34 electrons in Cl2. So Br2 has a bigger electron cloud, and so it's going to have stronger dispersion forces. That means Br2 has the stronger IMFs and the higher boiling point. For C, CH3OH has that OH group, so it has hydrogen bonding, dipole-dipole, and dispersion forces. Anytime we have hydrogen bonding, we'll have all three forces. HCl is polar because we have this difference in electronegativities, so it has dipole-dipole and dispersion forces. Comparing the size of the forces, these each have the same number of electrons, probably similar dispersion forces. Dipole-dipole force is likely to be similar, maybe slightly bigger for CH3OH because oxygen is a bit more electronegative. And so the key difference then is this extra hydrogen bonding force. That's going to make the total IMFs in CH3OH much bigger than the total IMFs in HCl. In this case, yeah, hydrogen bonding is very strong, and that's going to cause CH3OH's boiling point to be quite a bit higher. But you should remember to always check those other forces too. For D, our analysis looks basically the same as C. CH3CH2OH has these extra hydrogen bonding forces compared to CH3OCH3. Now, we do need to compare the size of dispersion forces, but if we just look at these molecules by eye, they're all, group 2 elements, and so these are basically a very, very similar size for each of these molecules. So because their electron clouds are similar in size, their dispersion forces should be similar. Extra dipole-dipole forces, extra hydrogen bonding forces will give us a higher boiling point for CH3CH2OH. Okay, next for E, CH3OH has all three intermolecular forces. Hexadecane is a hydrocarbon, so only has dispersion. So if we analyze the size of each IMF, hexadecane has much stronger dispersion forces. Remember, every time we make the molecule a little bit bigger, we get bigger dispersion forces. So this is going to have absolutely gigantic dispersion forces because of how big it is. When two of these hexadecane molecules come next to each other, we get huge attractive forces there. CH3OH does have extra hydrogen bonding and dipole-dipole forces, which would be definitive if the molecules were pretty similar in size. But in this case, these dispersion forces just win out, which is what happens when the molecules get really, really big. This is sort of like candle wax. So this is a solid at room temperature, whereas methanol is a liquid at room temperature. So hexadecane is our answer. Again, that's why we always need to compare the size of the dispersion forces to see if that's going to determine things before moving on to these other forces. Okay, so here's our key summary slide of the different types of intermolecular forces we have, and here's a little bit of a summary of some of the key information about kinetic molecular theory and analyzing the boiling points of different compounds.